Just 1 second, it's going live. Okay, we're live. Okay, we're live. Just gonna check it works before we get started. Just 1 second, it's going live. Okay, we're live. Okay, it works. Okay, so hello everyone. Welcome to this meeting. My name is Maxime Bravo. I'm the organizer of the AI and NLP meetup. And today we have a talk titled Data Science Tricks with the Single Decision Tree. Our speaker, Dr. Dan Steinberg, holds a PhD from Harvard University in econometrics and was the founder of Salford Systems, one of the world's first software companies in the field of machine learning. Working closely with Leo Bremen and Jerome Friedman since 1990, Salford introduced commercial software based on Friedman's proprietary code for CART decision tree, the first gradient boosting machine known as TreeNet, and Bremen and Cutler's random forests. Dan led the teams that won the KDD Cup 2000 predictive modeling competition and also the 2002 Terra/Duke Churn modeling competition, and was involved in a number of other subsequent competition winning efforts. Besides software development, Dan has been involved in major consulting projects for some of the world's largest banks and has published in economics, statistics, and computer science journals. Salford Systems was acquired by Minitab in 2017, and as of March 2020, Dan is the founder and CEO of Choice Analytics, Inc. And without further ado, Dr. Steinberg.
Thanks very much, everybody. I can hear that there's a little bit of a wobble now and then on the sound, so I will try to go just a little bit slower in order to allow for that. Okay, so I used a slightly different title on my slides, and it really is an alternative of the same thing, why data scientists should leverage single decision trees. I happen to be using the original CART decision tree because it has features that make my life easier, and you can use the same thing. I'll show you later how to get that, or you can write some of your own code around the open source trees. So let's just start by reminding ourselves the single CART decision tree is surprisingly useful. Data scientists are naturally attracted to complex, sophisticated, and high-powered tools. And of course, there is increasing complexity, and the research pushes us in that direction. But it's important to know when to use simpler tools. There's often not only no need for overkill, but the simpler tools can actually often give better results. It can deliver them faster, and it is often easier to communicate the results. So some of my results here are based on work that I've been involved with for the last 25 years. It's not just me alone, it's with some colleagues as well. And my history here goes back starting in the consulting world using these tools for our clients. It goes back 25 years. So just to remind you of what a decision tree looks like, this is not my tree. It happens to be part of a paper which wanted to show the use of trees in trying to predict whether someone who shows up at the hospital and is positive for COVID-19, whether they are admitted to the hospital or not. This same paper had another one then to indicate whether there was a bad outcome for that person, but this one was hospital admission. We don't want to go into this one. It's just a reminder of what these trees look like. And you could see that we start with all the data at the root node, then we make splits. The splits are always binary. And we finally end up with a pruned tree, which may not have equal depth going down each of the branches. So what made the original CART tree so revolutionary? It's good to remember this before we get started. So first of all, it automatically handles a mixture of different data types. So the data could be ordered, it could be numeric, that is, categorical, labeled, A, B, C, D, or 1, 2, 3, 4. Text data, in my case, the version that I used automatically converts the text to categorical. And all this is handled automatically. I think many of you know that there are a lot of learning machines which won't allow you to use categorical data unless you do some pre-processing, like exploding the variables into one-hot encoding dummies, which can be very inconvenient when there's a lot of them. CART also has built-in feature selection. It's oblivious to outliers, and scaling is totally irrelevant because the tree only sees the rank order of the data. It has some elegant missing value handling, which is local. So it's node specific. And the tree actually prepares for possible future missing values, even if the training data doesn't have missing values. And that's unique to CART. No other learning machine has that. A lot of data science articles, research have really worked hard to try to deal with highly imbalanced data. That you have rare outcomes. And you can see people doing things like trying to artificially resample the data so that the data becomes more balanced. That's totally irrelevant, unnecessary for CART. That will do the automatic rebalancing for you through weighting. Zero data preparation is actually a realistic option with CART. In fact, we often use CART without any data preparation, and I'll explain why in a moment, whereas that's really not possible with other learning machines. It's just you will end up with crashes, junk, and nothing that you really work with. There's also self-testing in CART. So there's a lot of benefits there. I'm going to skip this particular slide here and move on. So one of the things we've often done is we've used CART for your very first learning machine model. That is, when you first start looking at your data. Obviously, you do want to have a look at some summary stats. You want to make sure you actually have the right data. You have the data that you think you want to analyze. But then launching with a CART tree can actually show you importance of data. And it doesn't matter if your data is actually highly flawed, because CART will actually start showing you some of the flaws, and you'll get that feedback within minutes. And so you're on your way to perfecting that data to the point that it could be used by other learning machines as well. So here is the first example that I'll show doing that. In the year 2000, the KDD Cup 2000, which is launched by the Association for Computing Machinery. They don't do these things anymore now that there's Kaggle. But back then, they arranged, one of their members got data from a website. It was an e-commerce website, and they published the data, made the data available to the competitors. And the idea was to develop one or more predictive models relating to on-site e-commerce behavior. And one of those was to predict whether, if someone was attracted to the site, they left right away. That's predicting bounce. And then others involve things like predicting which departments on the store a person might visit, dollar spend, if any. And it turned out that of the 5 competitions, we entered 3 of them. We came in first place in 2 of those 3. So that was a very exciting time, a very interesting piece of work. So one of the things we did very early on in working with the data is we built a model to predict whether a person buys something or not from the website. Obviously, something that e-commerce decision makers would want to know something about. But when we ran the model, the first thing we noticed was there was something obviously seriously wrong with the data. So here is a version of the tree that shows what that problem was. So our target variable was the visitor purchased something from the website. And the root node split is made on whether the person was registered or not on that site. Now, that makes a lot of sense because think about your own behavior. Why would you register on a site if you didn't have some above average interest in that site? And this is a site in which the only reason you go there is presumably to shop or to browse. But if you register, your connection to that site is stronger. So naturally, if a person is registered, we would think they would be more likely to buy. And so that split, registered versus not registered, makes a lot of sense. And we have an idea about which way the split should work. Then, among the people who registered, there was another split made on whether the person lives in California, actually it was California or New York, or lived elsewhere in the US. And what has always been the case is that the level of sophistication and trust maybe in the internet back then, 20 years ago, was higher on the two coasts, and there's still clear differences in behavior between people that live on the coasts and elsewhere. So we weren't surprised by that split either. But when we look on the other side of the tree, we see the exact same splits being made. We see a split which is based on where the person lives. Here's the problem. If a person didn't register on the website in the year 2000, there was no way for us to know where they lived. Now today, with tracking and keys and the sophisticated ways of essentially spying on you or allowing people to spy on you, they might know today, but not back then. Back then, if you didn't tell them where you lived, and the only way you could tell them was by registering, then basically that information would not make it into the logs. The only thing we would know about you is the time of day you visited, the browser that you used, and your behavior on the site, which pages you visited, how long you spent, etc. We would not have any clue as to where you live. And yet here, the tree was saying that we did know. So what was the problem? The problem was that there was a flaw in the registered flag. So when the data said not registered, that wasn't always the case. Some of the not registered people had actually registered, and then CART was leveraging that. So instead of just sticking with this tree, we informed the organizers of the competition. They went back into the data, they corrected the data, and then they published the revised data set. This is very early on. This is within the first couple of days of the competition. So that is a way of using a CART tree to look at your data for the very first time. So you can think of this as CART being a generic data error detector. So, and it does require the human in the loop, of course, because the CART tree is only going to be aware of its performance. So what else can we use to determine whether there's something peculiar or not in the data? Well, that is the human looking at the tree. And you may look at the tree and say, wait a second, something is logically impossible or counter to the rules governing the data. That's what we saw on the last slide. Or we could just see something that is extraordinarily unexpected. So we know that there's a lot of important variables because we've worked in this field before. And now we see a variable that we would never expect to show up in the root node of the tree, and yet there it is. And we had that as an example. We were doing this work for a very big US-based bank, and they brought us some data, and they said, we know there's something wrong with the model, and we've already hired 2 independent consulting companies, big name consulting companies, and we asked them to tell us what is actually going on. Neither of them succeeded, and so then they came to us. And so we had the issue resolved within a few days, and it basically came down to this. When we ran the CART tree, we saw a variable that while potentially relevant, there was no way that it could be as important as it was showing up in the tree. And so we required them to send us the source code for the data prep. And what we discovered was that the data was managed in two different tables. You can imagine this would be the case because they had a responder and a non-responder group to a marketing campaign. And responders are usually a very small fraction of the data. So those are kept separately, and then you might have follow-on information about them. And for the non-responders, maybe you have nothing in terms of extra information. So they were handled in separate files, and we discovered that the source code for preparing the variables differed very slightly for this one variable. And so the CART tree detected that difference, and it said, well, I know how to distinguish responders from non-responders. The responders have this variable defined in one way, and the non-responders have it defined in a slightly different way, but that's enough for me to glom onto it. So again, we discovered a problem that other big teams had spent weeks working on and couldn't find it, and we got there essentially out of the box just by using the tree to start with. So here's another example, answering various ad hoc questions. Now, a lot of people do their ad hoc question answering by SQL queries, and there's nothing wrong with that. The only problem with it, it's very manual and it's very slow. A CART tree, although you may not see this explicitly, but a CART tree on the kind of data that I was talking about might, within a few minutes, have actually worked its way through 100,000 SQL queries. You're going to pick just a handful at most in that time. So it's searching for something. And so it does all the searching for you. You can follow up with SQL queries, but this is obviously going to move you to the right kinds of queries very quickly if you run the CART tree first. So in this case, what happened was this was an overseas insurance company had discovered that some of its policyholders had received unexpected notices of sharp premium increases. Some people got them, some people didn't. The management did not have a clue as to why this happened. They tasked some business analysts to find out. The people had been working on the problem for a couple of weeks and still hadn't been able to figure it out. So their top data scientist overheard them talking about it at a coffee station, and he said to them, look, I think I can help you. Just give me 1,000 records for each group, those that got the premium increase and those that didn't, and give me everything that you can find in your data. And obviously, we're not trying to build a predictive model here. We're trying to do some sleuthing of data. We're trying to do detective work. So he ran the model, and what came up was not anything that's exciting as a story, but what he detected was that there was a specific computer center which was responsible for all of the price increases. Now, you might think someone else should have been able to figure that out some other way, but they didn't. And so once he was able to tell them that, then they were right on the right track. And I don't know what happened after that, but I assume it was an easy thing for them to fix. So the next use that we make of CART, or that I have made of CART over the years, is to reject features. Now, feature selection is a huge area. You can find, I'm sure, hundreds of papers on this topic, and there are dueling methods of how to go about this. Usually, people are trying to eliminate variables that they think are not useful, and they want to pre-filter them out of the analysis. We never thought that was a good idea. What is much more important is to get rid of the variables that are too good to be true, or in other words, variables which probably have got something wrong with them. Often that is, they contain information that's leaked from the target. And sometimes it accidentally involves data from the future relative to the time that you have to make your predictions. We had that happen once when we were working many years ago with a catalog company. We had to predict who would buy what for the Christmas catalog, which was mailed, I guess, in early November. And we had to make those predictions in August because they had to prepare for how they were going to print and then distribute those catalogs. In any case, by accident, information from consumer purchasing in October ended up in the data set that was given to us. And so here's the problem. All the data came from the previous year, so everything was from the past. And the data from October was clearly before Christmas, so no problem there either. But the prediction had to be made in August. So a prediction that is made in August will not have access to October data. And if you give it October data, you're giving it an unfair advantage. And when you go to actually score data next October, next August, you're not going to have it. And that ends up possibly ruining your model, giving you overfitting at best. So what we do is, if you run a cart tree and you do a depth one tree, so you're only going to make one split. But in classical cart, you get a ranking of every variable that is available to split the root node. That has to happen anyway. That's the only way cart can figure out how to split the root node. It does a trial on every variable, and then that information, in our case, is kept, and then a ranked list is displayed. Now, if you go through the math of improvement scores and the Gini criterion, you'll be able to see with a little bit of experimentation that numbers that are greater than an improvement score of 0.1, 0.12 are probably problematic, not always, because there might be a super good predictor there. And you don't want to throw away a super good predictor just because it's good. But there are a whole lot of variables here, and I've blanked out the variable names in this slide, but you can see there's a whole lot of variables. If you look in the improvement column, the highest is 0.18, which is well above the 0.10 or 0.12 threshold we often like to use. And when you go down to the 29th variable, it's still above that threshold. So what we will often do is simply drop all those variables right away. We'll come back to them later because we want to investigate each one to see if it's really valid or not. Before dominating the model by super powerful variables, we want to see how the other variables can perform. And also make sure we can be sure that we haven't thrown in anything that really doesn't belong. We might have thrown away something that does belong, but we'll find that out later. Another approach is, instead of running one tree over all the data for all the variables, you can run a separate tree for every variable and just make it very shallow. Let's say a depth 2. So give you a little bit, or I show here depth 3, give you a little bit more investigation of the variable. And there again, what you can look at is just, this is ROC over here. If I saw an ROC here of 0.9, I would start to get a bit concerned. One variable getting you up there, a whole model getting you up there, that's one thing. One variable is another thing. Okay, another use is detecting unwanted signals. There are many cases where we have two partitions of data. Those could be two different files. They could be described in different ways. For example, they could come from different years. They could come from different, well, let's just say different years. The idea here is that the data is supposed to be extremely similar. Now, obviously, when you look at time series, something dramatic can happen, like, for example, COVID-19. And that could essentially change everything. And so the past becomes largely irrelevant to the future. But in other circumstances, when things are look to everybody to be relatively stable and the world is pretty much the same from one year to the next, then you expect your data to look very similar from one year to the next. And in fact, we're counting on that for classical machine learning modeling. It could be, and this is where we've often done it, is if somebody gives us two data sets, one called train and the other called test, and the training data has the dependent variable, but the test data does not. The idea is that they want us to build our best model, score the test data, and then send them the results. And they have the dependent variable, so they can then see how good our scores are. But they don't want us to have access to it. And then they'll know for sure that they've got an honest assessment of how good our model is. What we've always done in that kind of circumstance is we've built a model to see if we can distinguish between the two partitions. Because if I give you data, let's call it partition A, and I say I want you to learn from partition A, but then I want you to use what you learned from partition A to predict on partition B. And you look at the data and you say, well, partition B doesn't look anything like partition A. It's totally different. Then you would expect that your model is going to have a much harder time of doing well on partition B. Now, you obviously want to ask a question of whoever gives you that data. The first question is, are you aware that these two partitions are dramatically different? And maybe even how they're different. If they're not aware, then there's an error, and you've caught that error before you even launch into the whole complicated modeling process and then attempting to make your predictions, because you know right away that there's something problematic there. If, on the other hand, you're told, yes, we know it's different, then you may have to start spending some of your time trying to understand exactly how are they different and what will that difference mean for any model that you built on your first partition. So let's suppose that we're expecting that the two partitions really are essentially the same. So in statistical talk, these are observations both drawn from exactly the same parent distribution, same population. If CART says there's no difference, then you're good to go. Even though CART is not as powerful as some of the other learning machines, it'll run fast. It's a very simple tool to do a check. If CART says I can't find anything, in my opinion, no other learning machine is going to find anything either. Now, if CART finds something, then other learning machines will find probably even stronger signals, but that doesn't matter, because if you found something that's enough to be worried about, then you can actually start your next stage activity in response to that right away. You don't need to necessarily go to the high-powered models. I'll skip a slide here. Now, this one I think is really unique, and maybe unique to the original CART as written by Bryman, Friedman, Olshan, and Stone. And it is different than the open source versions. Open source versions are decent, but they don't come with all of the capabilities or tools and enhancements. And there's some real magic in the original version, the code was all written by Jerry Friedman. And one of the strengths is its ability to handle a many class classification. So what I mean by many class, I'm thinking here on the order of hundreds. Sometimes people think of many classes 3, 4, 5. That's fine. But as you start to push that number up, it becomes progressively more difficult to find the tree that can actually handle these problem as well. So in this particular case, this was real work. We had a manufacturer that wanted to model the consumer choice of a new product from a menu of over 200 similar options. And they got that data through a very intensive survey. They paid people a fair bit of money to take the survey, and they actually paid 50,000 people to take this survey. So this is really big time. This is 50,000 times in the neighborhood of $100 a survey just to the participant. Then all of it had to be processed. So we got that data, and we had hundreds of variables. And what we wanted to do was to understand that market. And so here you are with more than 200 different options. How do you boil that down to a story that people can understand? Well, it turns out that you can do an extraordinarily effective job with a single decision tree. Some other learning machines would actually have to build a separate model for every one of the options. And then you do things like rank the probability that a person chose a particular one from the hundreds of models, putting it all together in a way that you can absorb. I don't see an easy way you could do that, even a complicated way to do that. But the tree does it automatically for you. So let's have a look and see what happens here. This is an example. This is showing a little bit of a stripped down version. And what I'm going to do is actually zoom in on this part of the tree here. So what happens? As you move down the tree, you start in the root node where people are distributed across 200 options. As you move down the tree, as you go to one side of the tree, some of those 200 options are represented much more frequently than others. And some of the options just simply disappear. And what we were ultimately reporting were the top 12 in each terminal node. And so as you move down, and what we're using as predictors were actually characteristics of the consumers, including a lot of questions about what they liked and what they wanted and what they were looking for, and wants and needs kinds of questions. And so when you got to the bottom, you would see that there were a few distinct products that essentially dominated that node. And so what we would say is that people that had these certain characteristics were more attracted to these few products. And so you could think of those few products as also the ones that were competing against each other in the consumer's mind. What we discovered in our interaction with our client was something really interesting. We spent 2 full days with a group of about 20 people, and we walked through the tree, branch by branch. And at every terminal node, the people that knew the product and knew the market and were the in-house experts, they would say yes or no to the story that was being told by the tree. And they ended up rejecting about a handful of no's. There were some, they just didn't like the story. They didn't see how that could really be something that would work for them. But the rest of the tree became their marketing strategy for the rest of the year, because they could see what people wanted. They could see whether there might be some holes in the market. They could see what was probably really competing in the minds of the consumer with the product that they were trying to sell, etc. Some people say that, well, if a decision tree fits on one page, people can understand it. And if it has to be printed on several pages, then it's too big. And this showed us that that's really not the case. If you have reason to believe that the tree can actually communicate something of importance to you, then it might be worth 2 days of study to actually work through all the details. This is an interesting one, and it's actually based on a software trick, and it's not confined to CART, but CART does a very nice job here. So we'll go through this for CART, and it is unsupervised learning. So what are we trying to do here? We're trying to create a segmentation. Statisticians like to talk about clustering. So this, so far as I am told, this is an idea that comes from Leo Bryman, and actually it's not a new one. It's at least 30 years old, if not more, but I don't see it ever talked about in the data science literature for some strange reason. We start with a data set. So this is our actual real original data. What we do is we make a copy. This is the copy over here. But we don't leave the copy alone. What we do is we mess with the copy by taking each column and randomly permuting it. So what are we doing? Essentially, we're shuffling it. And we're shuffling it in place. And so when we're done, we have exactly the same values as we had before, but the values have been moved. So what used to be on row 10 is now on row 25, etc. We do that separately for each column. So when we do column B, we don't remember what we did for column A. We just start all over again with a new random number seed, and we continue until every column has been permuted this way. So what's the end result is that if you were to do summary statistics on these two versions of the data set, you do mean, min, max, standard deviation, etc. They're identical. Nothing has changed when you look at things in a univariate way. What has changed is how the values on any one row are combined. Because now, on the first row, we have the A value that belongs to row 2, and the B value that belongs to row 3. The C value comes from row 1, so that's the right row. The D value has come from row 4, etc. So what we've done is we've essentially messed up the integrity of the row. But the columns treated as a column are actually unchanged from the original data. Now what we're going to do is we're going to concatenate these two data sets. So we're going to put one on top of the other, and we're going to create a new label. The label will be original or copy. You could choose anything you like, 0 or 1, doesn't matter. The idea here is we want to build a model to see if we can distinguish between the original and the copy. If we can't, then what that means is that there's no inherent structure to the data. You could have value on any row, in any column. Knowing something about one row doesn't tell you about one column, doesn't tell you anything about another column. That's unlikely. Most data that we work with, if it's about the real world, has a lot of structure. So by finding a difference, the first thing we know is that there is some structure, but more than that, when we go down to a terminal node, we are going to see the exact structure that defines that node. And if the node is labeled as an original data node, if it's labeled as a scrambled data node, then what that tells us is that the data in that node is lacking the structure that we see in the original data. But instead of pursuing this particular example through to the end, what I'm going to do is do a variation of it. So it's the same setup, but now I'm going to show you how to discover anomalies or outliers. So we've done the same kind of model. And so what we're looking for now is terminal nodes that are defined as fake data, but they contain a handful of real data records. Why a handful? Well, if we find a lot of real data records, and what that means is we're really having some trouble distinguishing between real and fake in that region. But if the node is absolutely dominated by fake data, but a few real data records get in there, then that casts some suspicion about those records. Why do those records end up there? Maybe there's something sufficiently unusual about them that we should have another look. Maybe there is a kind of outlier or a bizarre pattern there that we really are not expecting, and maybe the bizarre pattern is there because of a coding error, a data error, or something else. But we have our attention drawn to it. So you can see how that becomes a methodology. And what's nice about this methodology, going back to what's strong about CART, we can have a mixture of data. So we can have categorical data, we can have numeric data, we can have text data, we can have missing values. All those things can be present in the data here, and we can do our either segmentation, clustering, or anomaly detection. We don't have to do any special data prep. We don't have to think about scaling the variables, which is important if you're using other types of clustering. All that's irrelevant. We just go down to the terminal nodes and look for things that are attracting attention to themselves. Okay, another use of this tree is hotspot detection for the two-class problem. Now, you could make any multi-class problem into a two-class problem by choosing one of the classes as the class of interest, and then everything else is not interesting. Normally, well, this is a difficult concept to actually grasp. My description of it verbally is not complicated, but there is a real important distinction here. A predictive model is generally evaluated over the entire range of possible outcomes. So if I'm doing some work, let's say for a lending entity, could be a bank, could be a fintech, and I am concerned obviously about default. If I'm going to lend people money, I want to get paid back. And I want to avoid lending money to people that won't pay back. So my default model, the typical default model, is going to give me a score which could range, let's say, from 0 to 100, with 0 maybe being the belief that this person will never default, and 100 meaning this person for sure will default, and anything in between. So you might say, well, that's all I need. If I want to find the people that are most likely to default, I just build my model and then I go to the highest scores. All that's fine, and you might have a very complicated model to do that. But let's suppose you're looking for some simple rules that you want to give to people. Let's say they're salespeople or they're people working with the public somehow, and you want to identify rules that tell you that certain people are just unusually likely to default. So when we do hotspot detection, we're building a special kind of model that doesn't care about the middle of the distribution. It doesn't care about moderate risk. It doesn't care about low risk. All it cares about is high risk. And it wants to make a distinction between ultra high risk and everything else. And in doing that, it might build a model that for general use is not very good, but it's extremely good for identifying the riskiest cases. So the way we do that is slightly counterintuitive. Priors, you can think of them as weights. They weight the classes or every record in the class up or down. And if you want to do hotspot detection, then you take the class that you're interested in and you downweight it. You might think, oh, well, I should be upweighting it, but that's not the case. You actually want to go in the opposite direction. So let's go through an example here. Suppose our data shows a default rate on credit card debt of 4%. In default cart, the way the tree works is if it can make a split, which makes one of the children have a default rate bigger than 4%, that's looking good. That is separating the defaulters from the non-defaulters. 4% is a very small number. And sometimes when we think about probabilities, we might think, oh, well, anything less than 50% is a zero. Not in this case. Anything greater than 4% is considered a 1, and everything else is considered a 0. So when we start with CART, we have these priors that are equal, meaning we treat each class as equal importance, and we do all of our calculations relative to the event rate of that class. So if we find that we go up from 4%, then that's default. If we go down from 4%, that means good. But if we change the priors, and we use an example here where we change them from 50-50 to 80-20, with 80 the weight on the goods and 20 the ones on the bads, then when CART makes a split and finds 5% default, that doesn't count as a default node. In fact, when you make an 80-20 priors weighting, you take the ratio of 2 to find out what happens. You're going to have to multiply that 4% by 4 in order to get a node that is considered a default node. So CART is going to start trying much harder to find nodes that have got a lot of defaults, because that's the only way it can make any progress. So here's what happens when we do that. Here are some examples of some different trees where I was using different weights. And what we see here, there's a tree that I like that happens to be the 80-20 weighting. Node 7 has, this is a relatively small data set, so you might not be impressed with the numbers. But what we find is that the bad rate in the learn and the test samples are very similar. And this becomes an interesting node to us. I've got some other trees where the bad rate in the node looks interestingly high, but there's a big difference between learn and test, and I don't like that. So in any case, if you use, let's look here. What's our base rate? It's 0.219. So we get that all the way up to 0.778. So that's a pretty big boost. When we build a CART tree with priors equal, our best node moves that up only to 0.479. So this business of manipulating the tree by manipulating the priors in order to find not a whole tree, but just one interesting node or one or two interesting nodes, that's an interesting trick, which I don't think, I've never seen anyone do but us. Okay, now we can talk about interpreting complex models. I don't think I want to say very much about that. I think that's actually a fairly well-known example. I'm just checking our time here. We're just about at 7 o'clock. So let me just go to the last few slides quickly and then see if there are any questions. I wanted to show you an example. The KDD 2009, that was an interesting competition in which people that used our software actually did pretty well. They didn't win. One came in second in one of the challenges, the other came in third. And then we redid all the analysis for another purpose. In any case, what we found was that our CART model on one of these targets that they wanted us to predict came in at just shy of 0.70. And I wanted to compare that with some of the other methods. Like random forest does only a hair's breadth better. So even though it's a darling, of the data science world, and often performs surprisingly well, this time it didn't really outperform the cart tree very much. So that suggests that there'll be times when your cart tree actually is quite respectable. Now, when you go to a GBM, then that move is from 0.7 to 0.76. Obviously, you're going to prefer the GBM, but at the same time, if you're thinking about, well, if I start with CART and do these basic first analyses with a single decision tree, am I going to be wildly inferior? Not necessarily, and you're getting other benefits. The competition was actually won by an ensemble of models, and mostly they are. So what I wanted to do here was to see, of the 123 different models that I built trying these different learning machines, I said, well, let's just take them all, build them on an 80% train set, and then just simply average their results in order to get an ensemble prediction and see how that does on a 20% holdout sample. And that gets you up to 0.79. So you can see it is actually a good thing to do if you're in competitions. 123 model ensemble is unlikely to ever be deployed in today's real life world. People have enough trouble deploying even one model. Just to point out a couple of things, these are the 4 authors of CART. So that's Leo Breiman, Richard Ocean, Jerry Friedman, and Chuck Stone. That's the alphabetical order. I'm used to it, BFOS. That's me in the background. That's Scott Cardell, who actually I've talked every problem I've ever worked with on data science through with him. He's responsible for a lot of our better ideas. And this is Richard Carson, a former student of Leo Breiman's, professor at UCSD, who actually introduced me to CART back in 1987. And he worked very hard to get my attention, because at first I wasn't paying attention. And he said, you have to. And he told me that often enough, I finally did. So the CART monograph, this was published in 1984. It's still available. This thing has been cited as of a couple months ago, 45,000 times. That's a big number by Google Scholar Me method. I think a lot of people cite it without reading it. I strongly recommend that you read at least some of it. The first few chapters are really quite remarkable in that they reveal the workings of a true data science genius, how he's thinking about, how am I going to analyze data? What are the issues? What are the strengths and weaknesses of some of my ideas here? And it's actually not difficult reading. The last part is very difficult because it's advanced mathematics for large sample theory statistics, but you don't have to read that. Then there's a couple of shorter expositions. This book, Top 10 Algorithms in Data Mining, which actually is also very well cited, has 10 chapters in it. Mine is chapter 10 on CART. And what I try to do is compress, but still be complete. And so it's about a 30-page chapter. And then that was preceded by a very brief article. And the article grew into the book. And so you're not going to find the detail in the article that occurred a few years earlier. And then there are some references that I have here. In terms of software, you can always go open source, of course. But if you want to use the original CART, which I think has a lot of advantages, you would find that in the Salford Predictive Modeler. It's a product that I worked on from about the late 1990s through 2016, when Salford was acquired by Minitab. So now you would go to Minitab, although this website still exists. And what you'll have to do is request. You get a 30-day free trial. I don't think they're ever going to say no to anyone. And you can just play with some of the features of cart there because a lot of things are pre-packaged for you. So you can do them very easily. Then if you decide you like something and you still need to go open source, well, then you've already seen how these things work, and then you can try to work it out for yourself. Okay, so that's the end of my slideshow here.
Yeah, thank you so much. If anyone has any questions, feel free to pop it in the chat. There is one question from Kunal Lalwani. He says, can the cart tree be used for finding the best chess strategies?
So actually, people did use a variant, a different decision tree. Ross Quinlan, who's responsible for a much simpler decision tree called ID3, used ID3 in order to analyze endgames. And I believe that the way these things work is that for every move, you have to give it some kind of score as to whether you're doing better or worse than before you made the move. I'm not. It's been a long time since I played chess. I used to be a chess fanatic when I was 15, but then I gave it up. So that's a long time ago. So I never tried to use machine learning for chess.
Okay. So let's see. It doesn't appear to be any more questions. But yeah, I mean, thank you so much for the talk, Dr. Steinberg.
Well, thank you for the opportunity, and thank everybody who came.
Okay, yeah. So I guess that'll be it for today.
Good night, everybody.
Thank you for coming, everyone.